So welcome on today's lecture. Last times we introduced the important concept that action of G on M, G is a group and M is first some set, and for us it is the most important example is a manifold. This is so-called left action, left, this is right action, and recall that left action is given by the property that if you apply it for an element which is a product of two other elements, it decomposes like that, and right action gives you the opposite order. And then there is a trick that you can construct LG from RG with -1 and opposite. We can change these actions if we need it. That if we have, in some situation, left action and we need right action, just do this improvement and you obtain the second one. What we already studied, that there are two consequences of any action, that on M, here you obtain something which is called orbits, and here you obtain something which is called stabilizer. Stabilizer for each point of M. And now we will discuss another topics, which is a consequence of any action, that how to construct a representation of G from action G on M. So first, what is the difference between an action and a representation? Representation is mapping from G to automorphisms of a vector space. And this RG is M from M. For us now it is a manifold. So here rho G, which is analog of this RG, is a mapping from V to V, and let's say, okay, say LG or also RG. So now this is representation, and these are two possible actions. So what is the main difference? That action can be treated as a generalization of a representation, or from the other side, representation is a special case of action. And what is this special case? That first, representation is left action by definition. It is not very important, but it is a convention that representation is left action because it is a homomorphism. And you can change it by G to -1 to right action, also representation. Then it is usually called anti-representation. Sometimes it is used, but it is not so frequent like the representation. So the first difference, so to speak, if any, is that it is left, always. But second, much more important, that it is an action in linear space. Here is an action on any set, or for us, the most interesting manifold. So here is also a manifold, but manifold very much more special, that is a vector space. So this is an action in vector space. And not only that it is an action on vector space, but it is a linear action on vector space. Because you can have vector space and action which is given not by linear operators. It is also possible. So representation needs two things from the point of view of actions. That first it is left, it is not very important, but which is very important is that it acts on vector fields by linear operators, on vector spaces, sorry, on vector spaces by linear operators. Yes, so representation is action left on V vector space by linear operator. This is the special property of representation regarded as an action. Yes? So it is also an action, but special action. Linear space, linear action. And now, what is our topics? That we have an action on M. So M need not be a linear space because it is a general action. Yes. General. And we want to construct some representation from this action. So, when we understand what we want, the first question is, what is the linear space for this representation? In which linear space it acts? This is the first question. And the second question, by which linear operators it acts there. So, now, when we are already here, our V is Fm. So, because our action is on some M, we do have this M, this manifold, say, and we have functions on this manifold. And we know that there is a linear combination possible on this function. Even there is a product, but now it is not interesting. It is an algebra, even more than linear space. But for us, now it is enough that it is a linear space. And notice that if M is a manifold, it is infinite dimensional linear space. So it is not completely like we studied this representation, usually finite dimensional. Now we will study for manifolds, we will study infinite dimensional representations, but we will see that they are inside hidden some finite dimensional representations as well. So it doesn't mean that we are leaving finite dimensional representations because of this is infinite dimensional representation. But it is simply, yes. And now the second question, what will be the linear operator? I will write element of Fm psi. So we have some psi function on M, R-valued function. And now we need to describe this operator, how operator rho g acts on functions in such a way that it will be a representation of this group G. And it turns out that the formula is extremely simple, that we need to define this function at any point from M. It is a new function. So there exists psi M, there exists this new psi. Yes, this is some psi, old psi, and new psi at M is defined as old psi at RGM. This is the definition. Or in shorter language, psi mg. This is just the other language or other notation how to write right action. Yes. So, in order to apply group element G via this representation on your function, you just apply this right action on the argument of the function. Yes, you change argument, and now we can check that by changing argument in this way, it is a linear operator. This is a question whether when applied on this, it works. So what is it? It is psi1 plus lambda psi2 at argument mg. Now this is the definition of the linear combination of functions, that it is psi1 on mg plus lambda psi2 on mg. And what is it? This is rho g on psi1 at m, and this is rho g on psi2 at m. So it is again rho g psi1 plus lambda rho g psi2 altogether at m. So we have this property which we needed, that it is this change of argument is a linear operator. It is the first property. Now the second property, whether it is a representation. So psi's form linear space. Yes? This operator is linear. So it is action by linear operators in some linear space. Now the remaining question, the only one, is whether it is a homomorphism, whether this is a left action. So what about this? By definition, which is where? Which is here? Which is here? Definition. It is psi at argument R, G1, G2 acting on M. But because this is right action, it is RG2 and RG1. So it is psi RG2 on RG1M. So it is rho G2. This can be written by some M primed. It is rho G2 psi M primed, but M primed is rho G1M. So it is rho G1 applied on rho G2 on psi at M. Yes, so we have this order as needed. Left. So notice that we obtained left action on psi's from right action on arguments. Yes. That if we used here in this definition left action on arguments, we will obtain right action on psi's. So in order to obtain representation, we need right action on arguments. Now, what if our action on our manifold is left by some in some natural way? Simply, we should use this G-1 trick, because here is a situation that if you want a representation, you need a right action. Yes. So if you have a left action on your manifold, you should change it to right action by the trick G-1. Now there is a question that what about its derived representation? Because we have a representation of group, we have also a derived representation of Lie algebra. It should be some row primed X acting in the same vector space like the original representation, so on functions. And the question is how it acts. So in order to understand it and to compute it, we have to, or not have, but it's very advantageous to look on this representation or on this formula in a slightly different way. Now, it's an advantage that we are experts on differential geometry already, so we know what is a pullback and Lie derivative and all those things. It should be, again, some linear operator on functions, that from one function you obtain another function, and the question is what kind of linear operator it is. So we can look differently on this definition. Yes, it is definition of this row. And if we look differently on this row, we will see very quickly a lot of interesting things, among them how the derived representation can be computed, and about the properties, and about very important object, which is called generator of this representation or fundamental field. So we come to the concept of fundamental fields. And in addition, we will come to a huge generalization of this formula, that we gain much more of representations, not only on functions, but only on tensor fields. Namely, that have a look what happens here, that we have that actually rho g on psi at M is this at M, and it can be written psi composed with Rg. Yes? This is the function psi composed with Rg applied on M. So without M, it is rho g. Psi equals this composition. But now, if this is a function, we know that this composition can be rewritten much more scientifically, that it is a pullback of this function. This is the very useful observation. So we can write it now without this psi. We can directly write this operator. So this is a new definition of the same thing. That what is this operator rho g on functions? It is the operator of pullback with respect with this action. We have mapping M from M. Here is Rg, this right action. So now we have functions here, and we can pull back them to the left, as usual. But now the left is the same like the right. Here is M, and here is also M. So it is a pullback of functions on the same M, by some mapping from M to M. And we know that pullback is a linear operator in general, yes? So we need not to check linearity, because we know from our knowledge from differential geometry that if you give me any pullback F star, it is linear mapping. But now we can, if you just see this formula can be realized not only on functions, but it can be acted on any tensor field. So we see that this formula is much more general than from which we started. We started that our vector space is Fm. It was up to now, yes? But now we see that if this is the formula, we can use it not only on 0,0 type tensors, but it can be also, so this formula also acts on any tensor field, higher, not only 0,0. And does it work in general? So first of all, it is always linear operator. Yes? So in this sense, this is a vector space, and this is a linear operator on this vector space. Now, is it a homomorphism from the point of this G? What is it? It is pullback of right action with respect to G1, G2. But because this is right action, it is in opposite order, G2 composed G1 and then pullback. But we again know how pullback acts on compositions, that it reverses the order once again. So there are two reversions of order. One of them is because we have a right action, and the second because we have a star. So altogether, we see that we have rho G1, rho G2. That means that it is a homomorphism. In practice, we will not, on this lecture, study this generalization to tensors. But it is useful to understand that it is that simple, that the same formula can be treated directly on any tensor field. And in the book, you have applications of this, that how this representation really acts on tensor fields of manifolds. But this is an introductory lecture. We just restrict to functions as we started. But also for functions, it is useful to understand this fact that it is just a pullback, because, for example, for computation of derived representation, it is advantageous to know it, that to compute it from this formula and not from that formula. And in order to do this, to compute this derived representation, we should have some small observation, namely that here is our Lie group, this E, and we know that there are interesting curves in this Lie group, GT equals E to TX, one parameter subgroups, yes, in the group. So now, if this group acts on M through some, say, RG, here is some M, and there is also a curve here, which is induced from this curve, that here you have some MT, which is MGT, or in this older notation, RGT on M. And what is GT? It is, again, exponential of TX applied on M. So what we do we have this one parameter subgroup. So for each t, we have a group element. And now we apply this group element dependent on t, the group element on the curve, to fixed m. So what happens? Because this group element becomes further and further from the unit element, it produces a bigger and bigger, still bigger action. At the start, at t equals 0, there is no action. We are just here. Yes, for t equals 0, gt is unit element of the group, and we have right action with respect to unit element, which is identity. But as t grows, this element is typically further and further from unit element. It becomes big element of the group, so to speak. So big element of the group produces big change on M, typically. We cannot measure it or needn't measure it how big it is, but it is intuitively clear that if this goes away from unit element, this goes away from original M somehow. And by some one precise curve. And it is true for any M. From M prime, it is here M prime T and so on. So what changes? The same operation acting on any element of this M. And now it is important to understand that we can introduce a flow as right action with respect to the group element E to Tx. So, or G, right action with respect to Gt, and Gt is one parameter group. The claim is that it is a flow. First, we prove it. And of course, this flow depends on this x. It depends on which one parameter group we study. There are infinite number of one parameter groups, and they are labeled by elements of Lie algebra, by this capital X's. Yes. So, for each x from Lie algebra, we have a one parameter subgroup. Put it as an element to your right action, and obtain some mapping, which can be denoted by phi given by this t and this x, which is here. Yes. Now, what about t plus s? So it is r g t plus s, but gt is a one parameter subgroup, so it decomposes to gt gs and also gs gt if we need. So it is what? Yes, it is r gt gs, and it is r gs r gt, and it is phi s x composed with phi t x. So we obtained it in reversed order, but it doesn't matter because it commutes, we know, yes? So the very important thing is that it is a flow. For each element of Lie algebra, we have a flow on our manifold. What does it mean? Any flow is generated by some vector field. So also this flow should be generated by some vector field, and because this flow is uniquely given by an element of Lie algebra, also this vector field should be generated by some vector. This flow, as any flow, should be generated by some vector field. Now this vector field depends on this x, because it is not just one flow, it is infinite number of flows for any capital X from Lie algebra. We have generator of this flow, namely some vector field. It is a vector field for which these curves are integral curves from the definition. So here, in this point, we have this psi x. Here it is also psi x. In each point of your manifold, you have a vector field given by this capital X. And this vector field is named that it is a generator of fundamental field. Of the action Rg. It is just a name, fundamental field. And sometimes it is also called that it is a generator of this action. What we see in a visual way when we are able to compute these generators, here are, this is M with this vector field, yes? So what we see intuitively this action, that how this action works, that if you know this vector field, this so to speak arrows on your manifold, you know the direction when the flow will go, that how the action works. The action goes in this way, simply, of the group. So, for example, if you compute all this is psi x here for fixed x from Lie algebra. If you have a basis of Lie algebra, you can compute these objects for 1, I is 1, and n, which is dimension of your G, which is the same as dimension of your this G. Here it is dimension of the Lie group as a manifold, and here it is dimension of Lie algebra as a vector space. The same number. So there are finite numbers of vector fields given by the number of the dimension of Lie algebra. For each basis of Lie algebra, one vector field. And if you know them, all of them, on the manifold, it means that at any point, if you visualize these vector fields, you see the direction from where you can go by the action. From the span, the linear span of these vector fields, just show you that from this point, by this action, you can go only in these directions. Yes, you cannot go orthogonally or something like that to this direction. So if the span of these vector fields is not the whole tangent space, you just see that which part of the tangent space is the possibility of going through the action of the group. So it shows you a visual picture of the action of the group very nicely. And these vector fields are called generators of the action. So what are generators? They are fundamental fields for basis of Lie algebra, not for any x, but for the basis. We will see that if we know, in a moment, that if we know these generators, we already know easily what are fundamental fields for any x, because there is a very simple formula for this. And from which side we know this formula? That now we want to compute rho x for rho g, rho primed x, the derived representation. So what is the definition? That rho primed x, one of the definitions, or the central one, is that it is rho gt, that etx. We remember that we usually did it by rho 1 plus epsilon x formula, that it is 1 plus epsilon rho primed x. It is quite practical formula, which means the same thing like is here. This is, it assumes that you know this, and you want this. This is a formula for how rho primed looks if you know how rho acts. Representation. That you compute rho for infinitesimal element, and it always will be of the structure unit element plus epsilon something. And this something is the operator which you need. But now have a look that our formula, it is general, yes? But what it is in the situation which we have here, that our rho is given by pullback of the flow. So it is pullback of R GT star but now notice that this RGT is a flow. Yes? So it is d over dt of some flow. Of pullback of some flow. And now remember that if we have a flow generated by some V, then d over dt at 0 of phi t star is by definition Lie derivative. Lie derivative is exactly this object. We had it. So what is the difference here? That just we want to know that what vector field is behind this flow. Namely this one. This is the definition of this vector field, yes? So what is it? It is Lie derivative with respect to fundamental field. Yes, so I will write it once again together, that if our rho g is Rg star, then derived representation is just Lie derivative with respect to fundamental field. This can be applied also in this tensor field case. So if our representation is given by this formula on higher tensors, it is Lie derivative with respect to this vector field. So to compute this vector field, we see that it is a very important thing to be able to compute this vector field explicitly for your action. That if you are given an action, it is some knowledge from this subject to be able to compute this fundamental field. It is something like ability to make differentiation of sine and apply or obtain cosine and so. So here, if you are given a formula for this action, of this action which Rg, of this action, this is the formula for the representation, and this is the formula that you have to compute somehow this vector field, and then make Lie derivative with respect to vector field. So in the simplest case, which we are interested, namely this one. We know that to compute Lie derivative is a simple thing, that it is just application of this vector field on function. So, in particular on Fn, where we started, and now we go back, it is that rho g on psi is either this on this just composition, in this case, and rho prime x on psi is, in general, Lie derivative of psi, but we know that it is just application of this vector field on your psi. The Lie derivative is trivial. And notice that it is very important, if you want to construct this representation, that you should have a right action. That then what if we have a natural left action? Just put g to minus 1. Yes? So I will now compute one extremely easy example for doing all these things, namely constructing the representation from some action and then finding fundamental fields. In particular, we will find these generators. And now, what about the vector field psi x if we know it only on the basis? So we remember that if this is really a representation, it should have these properties, representation of Lie algebra. Yes? And also that it behaves somehow on commutator. Namely, that it preserves this commutator. So these are properties of any representation of Lie algebra, denoted here as a derived representation from some group. But you can have separately representation of Lie algebra. This is the differential linear operator, which preserves commutator. Now, if it is true that rho prime x on psi is psi x on prime, you can discover that these vector fields, these fundamental fields, should have the property that they are linearly dependent on this parameter. This x can be treated as a label or parameter on this vector field, and we have a linearity with respect to this parameter. And if it is computed for a commutator, it is commutator of this fundamental field. Notice that here are completely different commutators. Here is commutator in your abstract Lie algebra. Here is commutator of vector fields. It is something different. Vector fields on manifold. On manifold, yes. So, what is the elementary consequence from this? If it is linear with respect to this parameter x, it is true that if this x is some xi ei, so if you decompose your x with respect to the basis in the Lie algebra, then the result is these constants times generators. So it is clear that if you know generators and you know the decomposition of your x, you trivially obtain psi x for any x. Yes, that the only thing to be computed are generators, not psi x in general, because it is then trivially computed. So this fact is a consequence of the linearity of psi x with respect to this psi. And this is also interesting property, which when your generators are computed already, and you want to check whether your computation is okay, then some small check is that when you compute psi on ei ej, what you should obtain psi ei psi ej, but this is a commutator of the basis in Lie algebra, so it is given by structure constants. And because of the linearity, they go in front. And psi on ek is in terms of commutator of generators. So what this formula says, that if you compute a commutator of your generators of the action, these vector fields, they should be the same, so to speak, as commutators of the basis of Lie algebra. So because you have known structure constants. So if you have a basis in your Lie algebra, you compute structure constants, yes? And this result shows that the same structure constants come when you compute commutators of your generators. That your generators are closed as a Lie algebra. It is a homomorphism that this to this is a homomorphism. It is given by these two formulas, that it is a homomorphism. So if you compute commutator here and you obtain some structure constants, you can do it in terms of your generators and you obtain the same structure constants. Yes? It is a simple check that you computed your commutators correctly if you know structure constants of your concrete Lie algebra. So now I will do in more or less detailed way one computation which is really very simple, and it shows how it can be done when it is simple. And of course sometimes we are forced to do it for less simple cases. But first we have to know how to compute simple cases in order to compute more elaborate cases. So this simple case will be given by example left action of GA1 R on R. This I don't remember whether I denoted in this way. Here I mean GA and R is affine group. Maybe I denoted in some different way, I don't remember, because I use two notations. Here it means the general affine, and also sometimes I use that affine linear. So I don't know what I used yet. GA, okay. So what is this GA on R that x goes to AX plus small a? So an element of this group is given by this pair. And we know, here this is from Rn. Yes, so a column goes to a matrix plus another column, X, by element AA. But we know the trick, which we now use, that this pair can be mapped in this way to a bigger matrix, n plus 1 times n plus 1, and it works as a homomorphism. So instead of this group, we can use the group of these matrices. We had already, I remember that we had it in a written examination, yes, some exercise on this. So now what about n equal 1? And by the way, how this works, it works that x1 goes to a small a 0, 1 on x1, which is, as we see, ax plus a1. So here is the group, and here is the action. Now, what about n equal 1, which is here? This block matrix now is 2 by 2, and I will denote it AB01. And AB are real numbers now, because in general it is n by n matrix and a column. But now for n equal 1, n by n matrix is just a number, and the column is again a number. Yes? So for n equal 1, the group is given by two numbers, parameterized. And this should be non-zero, because this determinant of A should be non-zero in order to create a group from it. So, as a group, now we have AB01. And what about Lie algebra? We can compute it easily, that this will be at G. Now take G equal 1, 0, 0, 1 plus epsilon something, some two things, and it should be AB01. This is the way how Lie algebra can be. This is from Lie algebra, which then will be called small ga, 1r. And you come to conclusion that Lie algebra is given by x, y, 0, 0, where x, y are general numbers, not no restriction to them, because it is a vector space. So it can be written, an element x can be written as small x times this matrix plus small y times this matrix. So this can be written as E1 and E2. We see the basis of the Lie algebra. And we can compute the structure constants. The only commutator which is needed, because it is two-dimensional, is E1, E2. And what we get, just E1, E2 multiplied, you get 0, 1 here. And I think that this is the result, which is E2. And it should be C1, 2, K, E, K. So we see that C1, 2, 2 equals to 1, and it is minus C2, 1, 2, and all others are 0. I think that we did this computation already, maybe in this written examination or not, I don't remember. Sometimes we did it. So I just recapitulate because we will use it. So what is now this action for one-dimensional case? That let this column be just number z, and it goes to this matrix, which is just a number now. So this is the action. It is LAB. It is left action. Yes, it is multiplication of this matrix from the left on the column. We know that such multiplication from the left directly by your matrix gives you left action. For our formula, remember that in general, rho g psi should be psi on right action on your argument. So we see the example that because this is a left action, it is something like Z1 goes to AB01 on Z1. Yes, it is a special case of this formula. So it is LAB acting on Z. And we need here right action. So we use the trick that compute inverse element and apply it from the left. So what about the inverse element? AB01 multiplied by A prime B prime 01. It is a special case of this multiplication which was done sometimes. Is A primed here, and here it is A B primed plus B 01. So from this we see that if we want this be chosen in such a way that we should obtain unit matrix, here we see that A prime should be 1 over A, and B primed, this should be 0, so B primed is minus B over A, and 0, 1. So our right action of element AB on Z is left action of AB to minus 1 on Z, and it is this matrix multiplied by a column Z1. Yes. Or where it is, this formula for A equal 1 over A and B equal minus B A. So it is 1 over A Z minus B over A, and that's all. So what about the representation? If you want representation of the element AB, I will write it in this way. It is representation of the group element given by AB. Yes, this is short notation. Here is the group element AB01. Applied on function psi. So this at Z is psi at right action on Z. And right action on Z is here. So this is the result, how explicitly our representation works on arguments. It works in this way on arguments. So it is the first part, or second maybe. First, think how the correct action is given, this right action. This is the formula on this manifold. Our manifold is, our G is that, where it is, here. So our G is here. It is GA1R, and our M is just R when we use coordinate Z. This is our group, this is our manifold, this is our left action, and this is our right action, improved by G-1 trick. So now we want to compute fundamental fields. So we have a group element near unity 1 plus epsilon E1. How it looks? It is 0, 0, 0, 1 plus epsilon 1, 0, 0, 0. So it is 1 plus epsilon 0, 0, and 1. So it is a group element near unity in the direction of the element E1 from the Lie algebra. Now, this is our G epsilon. How it acts on these functions. First, how it acts, what is the right action? Right action of this group element on Z. Simply put this as A and this is a B, yes, in our matrix. Our matrix here is the general form, but this element very near to unity in the direction of E1 has A equal 1 plus epsilon and B equal 0. So this action on Z is 1 over 1 plus epsilon on Z minus 0 over 1 plus epsilon finito. So what is this? This is 1 minus epsilon to first order. This is 0. So it is 1 minus epsilon applied on Z. It is Z minus epsilon Z. So what about psi? Psi Z with the representation given by element 1 plus epsilon E1. This representation gives you from psi Z, psi of argument Z minus epsilon Z. What is it? To first order, it is psi Z minus epsilon Z derivative with respect to Z of psi. It is first. What second? It should be, because we are represented this element, it should be 1 plus epsilon rho primed E1 applied on psi at Z. What is it? It is psi Z plus epsilon rho primed E1 on psi. So we see that what is then this? Here is psi Z, here is something, so without this epsilon, so this guy, yes, should be this guy. So we see that this is minus Z derivative Z psi. And then this is psi E1. It is the first generator. Generator which describes this element E1. So this generator is a vector field minus z derivative with respect to z on R z. What we should expect for each psi x, because it is a vector field here, it should be some function and this basis, because any vector field on this manifold looks like that. Yes? Now we see that our function is minus z for this particular vector field. Let's compute the second one. They are just two because we have two-dimensional Lie algebra. So repeat this, 1 plus epsilon E2. Here is E2. It is what? It is 1, 1 from this unit matrix. And I now epsilon here, so it is epsilon 0. This is group element near unity. What are AB of this group element? This is A and this is B. So what about this right action? Where it is? So this is in general the right action. In this case, it is what? 1 over A, it is 1 over 1 Z. B is epsilon, A is 1, so minus epsilon. Yes? So it is Z minus epsilon. It is the right action on arguments. So from this formula we see that representation for A equal 1 and B equal epsilon on psi Z is psi Z minus epsilon. But of course this is psi Z minus epsilon derivative with respect to Z, psi first, and second it should be what? It should be representation of this element rho of 1 plus epsilon E2 on psi on Z, which is by definition psi Z plus epsilon fundamental or generator psi of E2 applied on psi. By comparing, we see here is psi Z plus epsilon of something which we want to find. So it is this something. So the second generator is minus derivative with respect to Z. And now the check. We know that E1, E2, here it is somewhere, is E2. So the commutator of these two vector fields should be psi E2. What is the commutator? Minus Z derivative with respect to Z and minus derivative with respect to Z, or this check, so we don't know. It should be E2, which is minus derivative with respect to Z. And fortunately, it works, yes? Because this commutator is what? 2 minuses is plus, z, derivative z, and derivative z. Now you can invert it, minus z, z derivative with respect to z. And here, this x on this is 1, so minus derivative with respect to z. It is really this vector field. So probably we have a good result. So what is the general psi x if x is x1 e1 plus x2 e2? It is x1 times minus z plus x2 times minus z. So we see that in order to do these computations, you should just do infinitesimal computations always, which are very simple. So if you will have a look how the computation is done, it is very simple because it is infinitesimal. And to first order, you can compute easily everything. Now, more interesting example. So this is probably the most elementary example which I did yet. And now it will be also or more interesting, a bit more involved, but just still simple. And extremely important. That we have standard representation of G equal SO3 on M equals E3 or R3. That X goes to AX. Three-dimensional column goes to rotational matrix multiplied by X. And we already mentioned that it is left action. So what is the corresponding right action? We can already compute it. So this is LA, and the corresponding RA is A to minus 1 applied on X. And now, so this is already known example because we did it already. We did more general example when this A is from GL, namely 3R from, in this case. We did example GL and R on Rn. So here is how rotations act on Euclidean space. And the question is, what about fundamental fields and generators? So, what is the Lie algebra, SO3? There is a basis. It was, in which chapters it was done? 11, I think, yes? Done. Some times ago. In the first half of the semester, so you studied it quite a lot because of the written examination, which you already did. So you know this theory that everything about small SO3 and bigger SO3, this is the basis. It is anti-symmetric matrix for I goes 1 to 3. How they look like? Lijk is minus epsilon ijk, and Li Lj commutator was computed to be Lk, well-known commutator relations of small SO3. So, how element 1 plus epsilon Ni or Nk Lk acts on X. What is this element? It is rotation about N and angle epsilon. So it is infinitesimal rotation. This is some capital X. So this epsilon X is arbitrary small elements, arbitrary element of the Lie algebra actually, parameterized in this way, that small angle, unit, vector, and basis. This altogether it is capital X. It is capital X from SO3, and this is X from R3 when it acts. So we can compute what is, say, some M element of this. So it is delta M n on Xn, it is the first part, unit matrix, plus epsilon Nk Lk Mn on Xn. Just matrix multiplication. So this is, of course, Xm. And here is, what is this? It is minus Nk, and Lkmn is epsilon Klm. Notice that there are two epsilons in this game. Here is small number epsilon, and here is Levi-Civita epsilon. So completely different things. So it is what? Altogether minus epsilon Nk epsilon Klm x. Oh, sorry, K, not, it is Kmn. Kmn, sorry. Kmn xn. But notice that this is right action of this element. This is some A matrix. It is some rotation matrix, which is near unity, the most general one, 1 plus x, 1 plus epsilon x, or 1 plus something small times Lie algebra element. And so explicit formula is like that. It can be written, by the way, in terms of some vector product. Yes, it is some vector product of this n and this r vector. So it is something like r goes to r, and what kind of vector product? Well, it is m element, so it is epsilon m n k x n n k, so it is minus epsilon, and this is vector product r n. In vector notation it is this, in our component notation it is like that. So it is r goes to AR. Now we need A minus 1, inverse matrix. What is the inverse if this is the original just minus sign? Yes, we know it. So if I put it plus epsilon this expression, I will have already right action. So right action m is xm plus this expression. Epsilon n k epsilon k m n x n. So what is the representation? Representation of A on psi on R. It is psi on this of this R with plus sinus, plus sign. This is the change from left action to right action. And now the question is, what is rho primed of our element nklk acting on psi on R? So it is it should be computed from this formula by first order approximation. Yes? So this is the question. And in order to answer this, we should obtain psi at this argument with plus. Where it is written? It is here, this argument. N k epsilon k m n x n, which is what? It is psi r, this on this, plus all these together, epsilon n k, epsilon k m n, yes, x n, derivative of psi with respect to m. It is first order approximation, that original psi plus this additional term times the derivative. So it is, this should be altogether epsilon rho primed nklk applied on psi. So without epsilon, it is, we see the result, rho prime nklk is differential operator nk epsilon k m n, derivative with respect to m. Yes, so this is the fundamental field for this x. What is the fundamental field for just Lk without Nk? This is the fundamental field corresponding to Lk, or the generator, the kth generator, is this object without an x is somewhere, yes, here is, sorry, this xn. So what is it? K m n x n, derivative with respect to m. And just to inverse it, xn, so it is minus epsilon k n m xn derivative with respect to m. How can it be written? It is just something like minus r cross nabla. Yes. Here is a vector product. So it is interesting result because this operator multiplied by some Planck constant and so is just operator of angular momentum in quantum mechanics. Yes. So we see, of course, this is K component. I will tell the end of the story on Wednesday, yes, but have a look to this computation, that whether it is clear for you. And if not, of course, tell me then. So thank you.